What I like to do for the control engineering part of your module is to start by looking back on what topics you have covered in your second year in relation to the control engineering. And I know from my past experiences, it's normal for people to forget what they have learned once the exams are over. But we are entering your third year, and the topics we are going to discuss will be based on or built on top of what you've done in your second year. So it's quite essential actually to have a revision session on what we have done. But I'm not going to cover everything you did in your second year. Just a fairly brief recap of what was involved. And you will probably need a bit more time actually to dig up your second year lecture notes, presentation slides, that kind of stuff. Just go through them yourself and see how much you remember or indeed how much you forgot, so that you can actually pick them up again, and if you want to do well for this module. Okay, so I'll be fairly brief, but I probably will try to cover everything that we need as a basis for this module. Okay. Now, linear systems. We started by a discussion on linear systems in your second year. For the mechanical students, I guess the aero students will have a very similar coverage. A linear system is a system where the superposition or the principle of superposition applies. But essentially, when we say a system, and we think about anything that can be defined as an input-output relationship. So you could have a mechanical system, or you could have an electrical system, or you could have an airplane for aeronautical students. These are systems. If you provide an input, and the system will respond to give you an output. Okay. Now, in control engineering, in order to analyze the properties or behavior of such systems, we use something called model or mathematical models to represent the characteristics of a system. And that's what the process of building up this model is called modeling. And there are many different forms of models, and we have actually covered two of them. One is differential equations. The other one is the transfer functions. Okay, so but if you look at this block diagram, it's a very simple block diagram at the bottom. What's in the middle can be any system, but what we are trying to do is actually convert that system into a mathematical expression, so that for any given input on the left, and we can actually work out, or we can actually say, right, I actually know how the system will behave, what kind of output it will give us. So that's kind of stuff we need as a very early start of a control discussions. Okay. So, for example, here I have a mass spring and damper system, and the mass is connected to a spring and a damper. The other side of spring and damper are fixed. Okay, so they're not moving. Only the mass will move up and down. So if you apply a force on the mass from the top, then of course this mass will move, and the output, you will have an output of x. Okay, that's the displacement of the mass. Okay, now the movement is dictated by the Newton's second law, F equals to ma, but it's not just at F. Okay, it's also the spring produces a force against the movement. The damper will produce a force against the movement. So if you put all three forces together and then say F equals to ma, A is x double dot. X is displacement, x dot is velocity, x double dot is acceleration. Okay, you end up with the equation number 1. Okay, that is a second order differential equation. Defines the relationship between the input F, that's the force you apply, and output X. Now, the use of symbols X or F, anything like that, they are arbitrary. So I can use anything that probably more conventional to your application. So, but that doesn't matter. It's an input-output relationship we are looking at. So for any given input, if you can solve the second order differential equation, then you can find out how this mass will move up and down in response to the input x. Now, K and C here are spring constant and the damping coefficient. Okay, they can be considered as constant values. So that's differential equation, and that is this block diagram on the left-hand side represent the entire system. Okay, system doesn't have to be very complicated. In this case, we just have a very simple system, and it involves only 3 components. But the model can also be represented using transfer functions. Okay, and this we'll discuss a little bit more, but it's basically the equivalent of equation 1. So equation 2 is a transfer function of that system. It defines the input Fs and Xs relationship in the frequency domain. Okay, it's actually a lot simpler than the differential equation. If we want to find the responses in the frequency domain, we can use transfer functions. If that jogs any memory from your second year discussions. Okay, now where that come from? The transfer function is derived using the concept of Laplace transforms. Okay, a Laplace transform is something that you do in your math modules, and it is a pure mathematical tool. It defines the relationship. No, it doesn't define relationship. It defines signals in 2 forms. Okay, one is in time domain. That's your time domain, what you would normally observe, and then the Laplace transform is the representation of the same signal but in frequency domain. Okay, and in my second year, where I taught you guys for mechanical students, and I gave you this list. And for the aero student, if you don't have one, then you can use this one as well. What we have here is, say, if you apply the definition of Laplace transform to any time domain signal, for example, an impulse signal, delta t, the Laplace transform of delta t will be 1. Now you go backwards. If you know the Laplace transform of a signal is 1, then you will know its time domain signal is delta t. Unit step signal, 1. If the signal is a constant in time domain, then its Laplace transform will be 1 over s. Or if you see a 1 over s in frequency domain, then you will know in time domain this is equivalent to a step signal. A ramp signal t corresponding to 1 over s squared and so on. Okay, one particular signal you also need to look at is the exponential function. So if we have an exponential function e to the minus a times t, where a is a constant, then the Laplace transform of that exponential function is 1 over s plus a. Okay, so Laplace transforms are applied to signals. It converts a signal from time domain representation to the frequency domain representation. But the application of Laplace transform goes beyond that, okay? And we use this to derive our transfer function. But to do that, we need some properties of Laplace transforms as well. So if you look at this diagram, this slide, if we have a signal ft in time domain, and its Laplace transform in frequency domain fs, then the first derivative of the same signal in time domain actually correspond to the original Laplace transform times s. So d and dt in time domain actually correspond to s in frequency domain. So if you know the Laplace transform of ft, then you should know the Laplace transform of ft dot as well, because you just multiply that by s. If you have a second derivative, you multiply fs by s squared. If it's nth derivative, then you multiply fs by s to the power of n. That's derivative. Now, if derivative is multiplied by s in frequency domain, then of course integration is opposite of derivative. Integration would be represented in frequency domain by 1 over s. Okay, so bear that in mind. Derivative, every single derivative represents a single s in the frequency domain. If it's second derivative, you have s squared. Third derivative, you have s cubed, and so on. Every time you do an integration in time domain, it represents a 1 over s in frequency domain. Okay, so that's fairly easy to remember, but sometimes people get confused. Oh, which one is times s? So which one is divided by s? Think about that. Derivative, okay, d dot is multiply. F dot is the first derivative. F double dot is second derivative. We use dot is multiply. Okay, so that should help you to remember. Now from there, from the Laplace transforms, we can actually get to our transfer functions. Now, transfer function is basically a ratio between the Laplace transform of the output. Okay, so if you have yt, find the ys from yt. So apply Laplace transform to yt, you get ys. If you apply a signal to the system, xt, and apply Laplace transform to xt, you should get xs. Divide the two, that's your transfer function. So transfer function equals to Laplace transform of output divided by Laplace transform of the input. Okay? Or gs, if we use gs to represent the transfer function, ys is the Laplace transform of the output, xs is the Laplace transform of the input, then you have gs equals to y over xs. Or if we can actually write that equation in a slightly different format, or output equals to the transfer function times input. Okay, that's just a simple relationship for any block. Output, if we are represented in frequency domain, the output equals to gs, that's the transfer function, times the input. Now that rule applies to not only a single block. If you have several blocks connected together, it would also work. Okay, for example here, I have two blocks connected in cascade form, or sometimes we call it connected in series. Okay, now GS is one block or one subsystem. The input is US, the output is YS. Now USS actually comes from another block. Okay, US is also the output of KS of that block, of that subsystem. The input to this system is a different input, that's RS. So for each block, for example KS, we have the relationship between U, that's the output, and R. So U over R equals to K, or U equals to K times R as indicated in equation 1. Okay. For the second block, input is US, output is YS. Therefore, the transfer function GS equals to Y over U, or the output YS equals to transfer function GS times the input of US. So YS equals to GS times US. Okay. Now, if I substitute equation number 1 into number 2, so I replace this US by what's on the right-hand side of equation number 1. I get YS equals to G times K times R. Now, Y is the output here, R is the input there. If I can actually put a big block around, put a big block around G and K, I can consider this as a single block. Okay, the relationship between the overall output YS and the overall input would be defined by equation number 3. That's R input, that's Y output, G is a transfer function, K is another transfer function. But multiply them together, that will give you an overall transfer function, TS. Okay, so TS equals to Y over R, that equals to G times K. So you can actually, if you have two systems connected in cascade form, you can actually consider them as a single system. The transfer function of that overall system will be K times G. Now K times G. That's when you have two blocks connected in cascade form. But if they are connected in a closed loop, that gets slightly more complex. Okay, so if you have a K, a G, and an H in this block, but more importantly, R doesn't go into a block directly; it goes to a comparator. You subtract goes in there, subtract what is coming out at H block. Okay, and then the difference between two is fed into this KS block. The output connects to the GS. GS doesn't just feed to the output, it also feeds back to the HS as well. This is a typical block diagram of a simple closed loop system. Okay, where GS, we use GS normally here to represent the transfer function of the plant, which is the object that we are trying to control. HS typically represent the dynamics of a sensor measurement because we need some feedback. This is the feedback known as. Okay? And the output of the sensor is then compared with your input. Input is normally what you expect the plant, the GS, to do, or what you expect the YS should be. Okay? And the difference between the two, that's the ES. ES is known as the control error. Control error is fed into the controller, KS. It is the controller that determines what corrective actions should be taken if the error is increased, or error gets too big, or error is not within what you want the system to be. Okay, so KS is where it determines the actions. The actions is then fed into the plant. Say, right, I want you to do this, I want you to do that. Now, to derive the transfer function of that system, it's not simply just multiply the blocks or the transfer functions together. And what you would need to do is to look at two things. The overall transfer function consists from the input RS to the YS. If you want to define the overall transfer function between these two, it will consist two parts. One part is in the numerator. The numerator involves all the terms in the forward path from input to output. Follow the direction of arrows. Start from very left from your input, follow the direction of arrows, see what blocks you have until you get to the output YS. Okay, it doesn't go back, that's a forward from input to output. So in this case, I have two blocks in between in the forward path, so that's K and G. So you multiply these two terms together, stick that to the numerator. That's how you derive the first part of the transfer function for the overall control system. The second part is in the denominator. Okay, so in the denominator, put down first of all 1 plus. It's always 1 plus. Then the next term will be the product of all terms in the feedback loop. So identify a closed loop in your block diagram. So only closed loop I have, I can see it if I follow the direction of arrows. So start, for example, start from there, goes to the right through this K, goes to the right through this G. But that, if it goes out, that doesn't form a closed loop, so I need to come back. Come back, goes through HS, and then comes out again, go back to the summing block. Okay, so that forms a closed loop. Okay, now once you identify the closed loop, you multiply all transfer functions in that loop. Now in this case, I have K, I have G, I have H. So multiply three terms together, K, G, H. Of course, GS represents a transfer function of the plant. KS represents the transfer function of the controller. HS represents the dynamics of the sensor, or the transfer function of the sensor dynamics. So they are all transfer functions themselves, but we want to derive the overall transfer function for the closed loop system. So what you do then, from there, once you get to that stage, you substitute KGH into this, which will end up with a quite complex looking transfer function, because you will have fractions inside of fractions. Okay, then of course you have to use all your mathematical skills, try to simplify that transfer function, get rid of the fractions inside of fractions, and until you get to a form where you have S's on the top and S terms at the bottom. The only variable you have in the transfer function is S. Okay, all the others should be constant or coefficient or added numbers. Okay. Okay, so I've been bubbling on for like sort of 25 to some minutes, and take a break, and then you can start watching the second part of the revision. Thank you.